Okay, I've got this rather gorgeous question from the Estonian-Finnish Physics Olympiad. I can't quite remember which year it's from, but it's from a little way back. And as you can see in the question, you're given very little information indeed. You're shown a photograph that has this ruler in the foreground that's well focused, and a background that is clearly out of focus. The information in the question then says that you can assume that the image is created by a camera lens that's identical to one that would be created by an ideal thin lens of matching focal length and diameter. And all we have to do is determine the diameter of the camera lens used for the photo. This question I shared with a friend of mine, who in turn shared it with some friends of his who are keen photographers to see what they thought of it. And while they obviously have a lot of experience with taking pictures, they haven't necessarily studied physics. So I've made this sort of walkthrough of this question with them in mind. So I'll explain the physics behind how the lens works a little bit. If you have studied sort of A-level, possibly GCSE physics, it's on some specs. Some of this may seem familiar to you, but this is a pretty nasty little question, but can actually be solved using pretty straightforward principles. So without further ado, I'll start off by explaining how a lens in general makes an image. Then we'll look at the ideal thin lens, and then we'll have a look at actually how to solve this question. So first things first, how does a lens actually work? It's a pretty straightforward idea. If I was to cut through a convex lens, I'd see a piece of glass that has a cross section that looks something like that. I'll assume everybody's familiar with the idea of refraction. The way this produces an image follows the basics are this. Suppose here is a person that I wish to make an image of. The light from that individual will enter the lens. Let's choose a point on the individual. I'm going to choose the edge of their head here. Will spread out from that point and will enter the lens at various places. The lens, by refraction, will focus that light back in so that it ends up, these rays of light that I've drawn end up crossing at a point. And if I drew some other rays, for example, one that passed here, I would find that it would also obey that rule. So basically, whoops, let's just undo that. So basically, all of the light from a given point on the object ends up passing through a common point on the other side of the lens. And that is where the image is formed. If I repeated the process for every point on this object, if I did the same again for this point on the person's toe, I would find that all of those rays end up crossing at this point. And in that way, the image is formed. So the image in this case would be inverted. It would be an upside down little dude. And there is the image. The reason an image is formed is because if my eye is over here, there's my eye, and I'm looking at this, as these rays of light enter my eye, oh, I've drawn them in red, to my eyeball, it can't tell that a lens has done some kind of witchcraft in between. So as far as the eye is concerned, these rays of light have come from this point where they cross over. And therefore, as far as my eye is concerned, that is the source of the light, not over here. So that's how we can form an image, and you can try this with a magnifying glass or whatever. You know, if you're in a room with a window and it's sunny outside, go to the opposite wall to the window, hold a magnifying glass sort of parallel to the wall, and slowly move it away from the wall. And when the distance is just right, you'll see a nice crisp image upside down of the window formed on the wall. What you'll notice just looking at this diagram, if I was to move the object sort of towards or away from the lens, the place where the image is formed would also move towards or away from the lens, and that's important. So we'll call this plane in which the object sits, that is the object plane. This is the image plane, and that's absolutely fine. So let's go one stage further than this, and let's think about an ideal lens. An ideal thin lens is typically represented in the following way. Let's crack out a ruler here, and I'll draw this carefully rather than scribbled like I have above. Rather than drawing the glass, what we draw is just a straight line. Let's get a reasonably thin straight line, and I'll draw that here. There's the middle of it. Ooh, I can't draw on the middle. So there we represent the lens with a line, and we put little arrows like that at the top to show that this is convex lens. I'll also define the principal axis of the lens, and the principal axis is simply the line that passes through the center of the lens and is perpendicular to the plane in which the lens lies. I'll draw that principal axis. Let's draw that in very thin red. So this is the principal axis running through the center of the lens. So an ideal thin lens obeys two kind of important rules. The first rule of the ideal thin lens is that any ray that passes through the center of the lens will be undeflected, so it'll pass in a straight line. The second rule is that any ray that enters the lens parallel to this principal axis will pass through a point on the principal axis called the focal point. Here is the focal point of this particular lens. That's my focal point. And we can go a step further, and we can define the distance from the lens to the focal point as f. And that's generally called the focal length of the lens. So with that in mind, let's take a slightly more careful approach to how an image would be formed here. I'll draw in an object. Here is an object. Let's just go for a little person again. Here they are. It's a very small person. They're smaller than this lens. So as you can see in my diagram above, all of the light that leaves this person and enters the lens will end up focused on the same place. However, for our purposes, we're only interested in two rays of light, the two that we can predict. So the two rays of light that we'll consider are the one that goes parallel to the principal axis. I'll draw that in purple. Here it is. Parallel to the principal axis. And the reason we choose that one is because we know that that one has to pass through the focal point. So let's see where that is going to go. Hmm. 30 degrees on the money. So that ray of light is going to continue in that direction. The second ray of light of interest, because again, we'll choose it because we can predict what's going to happen, is the principal ray, and that's a ray that passes through the center of the lens. And the reason we choose that one is because, again, it's predictable because it will not change direction. So rays spreading out from the top of this little person's head, entering my lens, will cross this point, and therefore we know that that is where the image is going to be formed. I'm going to define the distance to the image plane as v from the lens, and I'm going to define the distance to the object plane as u. So the object is a distance u away from the lens. The image is formed at a distance v from the lens. It is possible with relatively straightforward trig, let me just move my ruler out of the way, with relatively straightforward trig to produce a lens equation. If you think of creating some right angled triangles here, I won't go into it in very much detail, but hopefully you can kind of, if you've messed about with some right angled triangles, you'd very quickly arrive with this. And that's this relationship, that 1 over v is equal to 1 over u plus 1 over f. That's the lens equation. In some cases you might see the u and the v on the sim side. I prefer it this way around. It's worth noting that u will be negative because we will be measuring displacement from the lens to the right being positive. So 1 over u is actually a negative number. So that's a useful thing to note. The feet will have to, these feet are on the principal axis, so the feet of my image will also have to be on the principal axis. So that's the lens equation, and that allows us to do calculations which predict things like where an image will be formed. There's another step that we can take while we're looking at this. If I just highlight the right angle triangle that sort of goes from the principal axis to the top of the image to the center of the lens, like that right angle triangle, and this one that goes to the object, those are similar triangles. Therefore, if I said the height of this object, if I call that O, and the height of the image I could say that the height of the image divided by the height of the object, which is generally referred to as the magnification, must be equal to v over u. That must also be true. Okay. Don't panic, mathematicians. That is an O, not a 0. I've not gone crazy. So now that we've kind of set up the equations that we need and we know how our lens kind of forms that image, let's go back and look at the question and see what it's asking us. We're trying to find the diameter of a lens, and we're assuming that the images created are identical to ones created by an ideal thin lens. We have usefully in the foreground, in focus notably, a ruler, and the stuff in the background is out of focus. So let me just talk momentarily about why the background stuff is out of focus. This equation shows us the relationship between focal length, which is fixed for a given lens. That depends on the curvature of the lens itself. The object and image distance. What if I had an image in this setup, if I had an object in this setup that was at a radically different distance? Well, what I would find if I draw, let's just draw something nice and simple over here. Let's draw a big arrow. Oh, it's too big. Let's draw a slightly smaller arrow. If I have an arrow that is at a different distance, if I was to repeat the process with my ruler, the top of the arrow line is roughly in the same place. So the ray from the top of the arrow that travels parallel to that principal axis is actually going to go along the same line as the one that I've already drawn for my original image. But this ray that passes through the center of the lens is going to take a completely different line. So therefore, they will cross over at this point. And as we can see, that image therefore is formed at a different distance. So we know that if I have my eye somewhere over here simply looking at these images, well, my eye will just think that that's where the light has come from, and it will happily refocus itself to suit either looking at this point or looking at this point. But if we're trying to make a camera, what we have to do is in this image plane, we have to insert either a piece of light sensitive film or an electronic sensor, a CCD, which will in some way record the light that hits it in a kind of pixelized way, and produce a 2D image at the image plane here. So what happens if we do that to this background stuff? Well, as we can see, the rays from that background stuff don't all meet in the same place. So this point, this single point of the thing in the background will have been spread out to much larger than a point, and therefore the background will be blurred. Hopefully that is very apparent in this picture. So that is kind of the crux of how we're going to solve this. So without further ado, let's actually solve this question. I'm going to draw a new lens diagram Let's get a principal axis on the go. Oops. That I'll draw in red. Here's my principal axis. Let's put our lens in. I'll try and draw this reasonably carefully so that it's clear. Nice thin lens. Okay. Let's put in a focal point here. Now, in my image, I have a ruler with convenient centimeter marks on it that is focused. So I'm just going to add in here I'm just going to add in here a 1 centimeter section of ruler. This is 1 centimeter in height. And then we'll draw in our rays and we'll see where that image ends up. So that is a 1 centimeter object. So again, the way we do this is we're going to draw in the 2 predictable rays. The first predictable ray, let's draw them in green, let's mix it up. The first predictable ray is the one parallel to that principal axis. And that's going to pass through the focal point. Because those are the rules of thin lenses. Rays parallel to the principal axis must pass through the focal point. So that's that one. The second ray that we're going to draw is the one that passes through the center of the lens. And those do not change direction. So again, nice and predictable. Where those rays cross is where all the rays from the object passing through the lens will cross. You've always got to draw arrows on your rays to show the direction of the motion of the light. Otherwise you get in trouble in Key Stage 3 physics lessons. So where does my image end up? It ends up here. And the particular distances I've chosen, it's actually slightly bigger. Let's call the size of this 1 centimeter I. Okay, so as a reminder then, this distance, that's u, and will be a negative number. V is from the lens to the image plane. F from the lens to the focal point. And my lens equation, I always seem to have to click twice to move this. My lens equation is that 1 over V equals 1 over U plus 1 over F. My magnification equation, if I apply this to this setup, I could say that I divided by 1 centimeter must be equal to V over U. Incidentally, since U will be negative, that means that, notice that the magnification is also negative, and that makes sense because my image is upside down. So don't worry too much about that minus sign, but it is worth noting that that negative means that the fact that I will have a negative value and U will have a negative value means that this equation is still valid. Okay, so that's what's going on with the ruler. Now let's think about the stuff in the background. This is the interesting stuff. This blurred business in the background. To answer this question, we will assume that that is a point source of light that has become a round circle. So we're going to assume that that is, for example, a light, a small sort of light source or a reflection It is a point source of light that is very far away. Since it's very far away, the rays that come from it when they arrive at the lens will be parallel. So the rays that come from that and enter the lens are all traveling parallel to the principal axis. So I will consider the two rays that enter the lens at the most extreme points, top and bottom. So there's one. Actually, I'll tell you what, why don't I draw these rays in a different color? Let's go with, I don't know, hot pink and slightly thicker so that we can see what we're doing. So these rays, and again, I'm only choosing to draw two because, well, that'll become apparent pretty quickly, I think. But the ones that are entering the lens at the extreme positions are the two that I'm going to draw. So here comes the light from a distant point source. Now remember, this light has spread out from a single point, but because we're so far from that point, it appears to be, these rays appear to be parallel. And they will be roughly. Because they're parallel to the principal axis, both of these rays therefore will pass through the focal point. Get my ruler at the right angle for this. There they go. I don't think I need the ruler anymore. So those are my two rays coming from a point source of light in the background. Now notice this is my image plane. Notice how much room that point source is taking up in the image plane. So let's call the height of this point source in the image h. That's what's recorded on the film or on the CCD of the camera. And let's call the diameter of the lens d. Again, by similar triangles, if we think about the triangle made by those 3 points, it is similar to this one. So therefore, I can say that the ratio of h over d is equal to the ratio of this distance, which is v minus f, divided by f, by similar triangles. Now that we've done that, it's time to put all of this together. So let's take the lens equation. I've got this expression that relates the size of a centimeter in the image to the ratio v over u. So let's multiply every term in my lens equation by v. And what I get if I do that is 1 equals v over u plus v over f. Substituting in, that is equal to I plus v over f. Okay. Now let's go down to this expression that I've written that relates the height of a point source in my image to the diameter of the lens. That's v minus f over f, which I can write as v over f minus 1. If I do a quick rearrange over here, v over f is equal to 1 minus I. Sub that in over on this side and get h over d is equal to 1 minus I minus 1, which equals minus I. Remember that I itself is negative, so this minus sign, if you like, evaporates. There's no problem there. What that means then is that the diameter of my lens is equal to minus h over I. The minus, I'll leave the minus in, but it's kind of neither here nor there. It doesn't matter. The image that we look at in the picture has been inverted for us so that everything looks the right way up. But the actual image formed inside the camera would have been inverted. So if I just drag this over here, what that means is that the diameter of my lens is the height of one of these divided by the length of 1 centimeter, and that will give me the diameter of the lens in centimeters. If I draw that pretty crudely across, I mean, feel free to actually take proper measurements, but by dead reckoning, that's somewhere in the region of 1.5 centimeters. And that's it. I apologize if it's a little garbled. I wasn't really sure how much of the sort of background theory and physics to explain, but hopefully, I don't know, hopefully you can follow that, and hopefully it's helpful. Cheers.